Next up, we have standing wave in a string. In the previous video, we covered the concept of superposition of waves. And one result of superposition of waves is the formation of standing waves. One example of a standing wave is standing wave in a string. In particular, this is an example of a transverse standing wave. Standing wave in a string. A standing wave in a stretched string may be formed by allowing the wave in a string, the wave traveling through the string, to be reflected from the far end of the string. For instance, let's say we have the far end of the string to be a fixed point. When the wave traveling down the string reaches that fixed point, the wave will bounce back, resulting in two identical waves that are moving in opposite direction in the same medium, which is the condition for forming a standing wave. So a standing wave is easily formed in our stretched string. Segments are formed in the string as a result. Comparing the segments formed in the string with the length of the string, so comparing length L with one segment, comparing the string with, say, two segments that are formed, and if three segments are formed, we compare the three segments with the length of the string L, and bearing in mind that for a standing wave, one segment is half a wave, half a wavelength, we get lambda is equal to 2L over N, where N is the number of segments that are formed in the string. If N is equal to 1, you have only one segment in the string. If N is equal to 2, you have two segments formed in the string. N is equal to 3, you have 1, 2, 3 segments formed in the string. So you have N is equal to 1, N is equal to 2, N is equal to 3, and so on. N is equal to a whole number or integer greater than 0. N is equal to 1, 2, 3, 4, 5, and so on. And since lambda depends on n, if we keep the length of the string constant, you have lambda n. Lambda 1, 2L. Lambda 2, 2L over 2. Lambda 3, 2L over 3, and so on. Our standing wave is still a periodic wave, so we use the equation for speed of a periodic wave. V is equal to F lambda. Using lambda n, we have Fn is equal to V over lambda n. And lambda n is 2L over n, which gives us Fn is equal to Nv over 2L. V is speed of wave in a string. V is just equal to square root of F over mu, square root of tension in the string, divided by linear mass density of the string. Thus, Fn is equal to N over 2L times square root of F over mu. And Nv over 2L may be written down as Nf1. And again, N is equal to 1, 2, 3, 4, and so on. So you have F1, F2, F3, F4, F5, and so on. This collection of all possible oscillation modes or frequencies, you have F1, F2, F3, F4, and so on. This collection of all possible oscillation modes or frequencies is called a harmonic series, with the frequencies referred to as harmonic frequencies. And the number of segments, n is equal to 1, 2, 3, 4, 5, and so on. Whole numbers or integers greater than 0, the number of segments n is now referred to as harmonic number. Take note of the following naming convention for the harmonic frequencies. Harmonic frequencies again, you have F1, F2, F3, F4, F5, and so on. F1 for one segment, F2 for two segments, F3 for three segments formed in the string, and so on. F1 is referred to as the first harmonic frequency or fundamental frequency. F2 is second harmonic frequency or first overtone. Overtone, frequency above the fundamental frequency. So F2 is the first frequency above or over the fundamental frequency. First overtone. F3 is third harmonic frequency or second overtone. F4 is fourth harmonic frequency or third overtone. And F5 is fifth harmonic frequency or fourth overtone, and so on. You still have F6, F7, F8, F9, and so on. And that's it for now. That's it for our discussion on standing wave in a string. We'll continue our discussion on wave motion in the next video, wherein we take a look at standing wave with sound, which is an example of longitudinal standing wave. So again, that's it for now, and thank you for watching.